I'm happy to have the chance to speak to you today about a topic which is entitled Study of the Structural and Electronic Properties of a Semiconductor Alloy of the 2,6 family with an AB initio study. We are going to divide this talk into 5 parts, starting with a simple introduction. Thus, we shall speak of semiconductor materials, more precisely of family 2,6. Then, we will focus on the methods and details of calculation, and we will finish with a conclusion. The main goal of material physics is to develop and ameliorate materials to gain new properties. Among these elements, we will focus on the semiconductor. Semiconductor, a material that has been studied since 1830 and considered as an intermediate between metal and insulator. Resistivity between 10 power minus 3 and 10 power 2 centimeter. At T equals 0 Kelvin, the semiconductor behaves like an insulator, but it conducts electricity as soon as the temperature increases. These materials are classified into several types: semiconductor in Callan 4, family 3,5, and family 2,6. These are made up of one or more elements of the 6th Callan with one or more elements of the 2nd Callan of the periodic classification. The majority of compounds in this family can be crystallized under two phases, zinc blende and wurtzite. Their interdict bands can constitute a loss. The latter are ideal for optoelectronic and spintronic applications such as light emitting diodes, short wavelength lasers, ultraviolet detectors, transistors, and heterojunctions. Among the major advantages of this family are high speed, low noise, and very high gain. Turning now to calculation methods and details. The calculations in this study are performed based on the density functional theory. We have employed the full potential linear augmented plane wave method. The exchange correlation energy is described in the GGAPB and TBMBG approximation techniques implemented in the computer code Win2K. Primary calculations were performed to study the structural and electronic properties of the binary compounds of family 2,6, CDS, CDTE, MGS, and MGTE in the zinc blende structure, in which the values of muffin tin rice and the number of key points are presented in this table. Besides, the following table summarizes the lattice parameter, bulk modulus, and its first derivative with some theoretical and experimental data for comparison. We note that the parameters are generally in good agreement with the theoretical and experimental results. Here we shorten the gap energies calculated by the GGAPB and TBMBG approximations. There is an underestimation of the gap energies for GGA and MBG compared to the available experimental results. It's clear that the MBG significantly corrects the energy gaps of the four binaries. Therefore, the GGA is no longer valid to reproduce the exchange and correlation potential. However, the MBG is used to find values closer to the experimental. To conclude with, this modest work provided a brief overview of the structural and electronic properties of the binary compounds of the family 2,6, CDS, CDTE, MDA